Alrighty then. So we're going to talk about another data structure. Some people call it an algorithm. I think the difference sometimes between algorithms and data structures isn't as clear as it could be. Just because they kind of could be thought of different ways. The one we're talking about today, I'm going to call it union find. It goes by two names, unfortunately. Sometimes it's called disjoint sets. Sometimes it's called union find. And this one is probably one where the terminology is the worst part of it all. Everything else is pretty straightforward, but the terminology is different depending on where you go. So quick reminders as always. So the quiz 6 will not include today's lecture. So it's just 21 through 23. So hopefully that lightens your load a little bit. Don't forget that is due on Tuesday. And then we got one of the many adventures of our quiz, our homework 6. So please don't forget about that. And next week, next Friday is last day to drop the W, just FYI, if you feel like you have to do that. Hopefully nobody's in that place. So hold on a second. Let me just kind of close our door here. Okay. Okay, so we're going to talk about really more connected components, but we're not going to use the connected component class to do that. So hopefully you guys are all starting to get more comfortable with what the idea is of a connected component in an undirected graph. And we're using the depth first search to kind of do that. Really, that's the tool that we're using in that class. Today, we're going to look at a completely different approach of doing this called union find. So union find is really not so much interested in the exact connection. It just wants to know whether two people are connected or not. So in my, this is my silly AI picture gone sort of somewhat haywire. So if you've ever played that game as kids where you have a cup with some string and you try to talk to each other, right? So typical situation is we've got this really crazy network out there and two people want to know whether they can talk to each other. And in the middle is this sort of dynamic change situation. There's more strings or more connections being added to the network all the time. So it's a little bit like that Verizon commercial where the guy's like, can you hear me now? Can you hear me now? Can you hear me now? So these networks are constantly changing in some way. So they are dynamically changing. That is a very different thing than what you are all doing with homework 6. Those networks are static. And then we do analysis on that established network to sort of learn some insights. And if you think about it, if we change the graph in homework 6 in the middle of your analysis, you would have to create a brand new instance of the connected component class. Union find is different. It's optimized to answer a connectivity question without having to go through a whole lot of regeneration of the analysis. So it's a completely different strategy, sometimes known as disjoint sets. And again, it is optimized, if you will, or kind of throws away any information other than just like, hey, can we talk to each other? So there's no way to find a path using union find. If I were to say, hey, can you use union find to find the shortest path between two people in a graph, you should say no. I mean, obviously after this lecture, you should say that. But otherwise, it's a lot like connected components. We're just trying to figure out, can two people, are they in the same component? Are they in the same island? And therefore, can they communicate with each other? And it turns out there are a lot of really cool applications for that. So we will look at strongly connected components. We'll look at this idea called percolation, which is very cool. And we'll look at a working model of something called the Monte Carlo simulation. And we'll actually look at our performance of this, which turns out to be constant time. So it's a lot like the symbol table in the sense that if we kind of manage our structure a little bit like balanced search trees, we can keep our performance really more or less effectively at a constant level. So no matter how many connections we have in our graph, we always are sort of basically paying a constant cost over the life of our graph. Okay, so that's really where we're going today. Just a reminder, as more of this terminology gets deeper and deeper, I do think it's easier to kind of go back and just look at our slides, especially for graph definitions. So this particular Quizlet actually looks at kind of where we've been and where we're going with our graph definitions. And I think that is going to be something that will help you, especially on quiz 6 and on the final exam. So please keep that in mind. It's always a good place to come back. And then for our lecture today, there's a bunch of union find questions that hopefully provide some, quick catch up if it turns out that you need that. So just let me know if you have any problems with any of that. So let's talk a little bit about connectivity. So network graphs, as we've talked about before, are a pretty big area of study. They apply to a lot of different areas. And so there is a question of shortest path, or what is the path? And I know some of you are doing that now in your labs, but there's also just a question of like, hey, are these two things connected at all in any way, right? And so we can model things like these protein interaction networks. We can model like biological ecosystems. Do these animals connect, or, does one animal feed another? What is the connection in that entire ecosystem? But we can also model materials like electronics. So electronics, if I'm trying to figure out whether electricity flows through a particular material, there's a certain sense of porosity. There's pores in that material, or maybe electrical conductivity in that material. So we might want to know, hey, can electricity flow through this thing? Is it a superconductor? Also, social interactions. How many connections on Facebook before we all know Kevin Bacon, or whatever that joke is, right? So all of these kinds of things we can kind of simulate. And we can also actually play some pretty awesome games as well, determining whether there's a solution. So very, very wide area. And dynamic connectivity is all about allowing the connections in the map to change over time and then keep answering questions, kind of like that Verizon commercial thing. Like, how about now? How about now, right? So there's a couple different ways we can talk about this connectivity or this dynamic thing. We can say that, we want to be able to add and remove edges dynamically and constantly ask questions. And that's sometimes referred to as full connectivity. So that speaks to one particular challenge, right? So that's like, hey, I'm going to add these and I'm going to take them away, and then I'm going to add some more, okay? There's a second one, which is decremental connectivity. It's like we're going to start with a graph, and then we're going to subtract things and ask questions. We're going to say, okay, now am I connected? Now am I connected? And the third one is the one that we're going to look at, which is incremental connectivity, where we are only adding things to the graph. Okay, so that is an area where union find really hits its sweet spot, and we'll see kind of what I mean by that. So always just adding more connectivity and then re-asking the question at some point. So I think the connectivity question is probably pretty, well understood now. We've covered a number of graphs, but it's really just about whether we can find any path between these things, okay? So in bigger questions, right, this is, about a million different connections, right? So we could try some brute force algorithms, but really, depending on the question that we're asking, we could do some things pretty efficiently. So asking, are they connected, is a very different question than asking, okay, what is the path, or what is the actual shortest path? So we've been kind of answering this question and finding the path using our connected component class. But today we're just going to ask ourselves, are they connected, and forget about the path altogether. And that's going to let us kind of like chuck out the extra passenger seats and the airbag and everything and go a whole lot faster. And that's what the union find data structure is all about. So down here on the bottom, depth first search, breadth first search, a full graph description. Those let us go a little bit deeper with questions, but we're going to kind of hover over the surface. So down here, our space and time complexity, we've said with our graph structure, is kind of V plus E, the number of vertices plus the number of edges. Up here, we're going to see that is effectively the logarithm of the total number of vertices. Okay, so we won't go into the analysis on that, but in our space is going to be just linear, right? It's just going to be however many vertices we have. So that's pretty good. That's definitely better than the stuff we were looking at on the bottom. Okay, so our worst case performance is actually going to be much better in a union find situation. We just can't really figure out what the exact path is. Okay, so these are just some of the possible applications. And the ones that we're going to see in this class in particular is Kruskal's minimum spanning trees. So this is coming up next week, and strongly connected components, a new kind of component that we actually haven't looked at using directed graphs. So far, all of our graphs are omnidirectional, right? You can travel either way between the nodes. Next week, when we look at these applications, we are going to have a tougher challenge. And so our union find, you will see it come back into some of our discussions and be used as a part of a larger algorithm. Okay. So just reviewing again, all of our nodes, as usual, we're going to represent them with integer values starting from 0, and there will be no gaps, right? So we will kind of know ahead of time how many nodes that we have, or vertices, if you will. And then we will assume, we can always hash those things into a name if we need to. Okay, so 0 to n-1 is still what we're kind of doing there. Our connections are still going to be symmetric and transitive. In other words, if this is connected to this and this is connected to this, then I will, say that those things are connected, right? I don't need to have an explicit connection there. Okay, so it's a little bit like symmetric operations in math. Okay, and we'll ignore any redundant connections. So if somebody says, hey, these things are going to be connected, it's like, well, yeah, I already knew that, right? So we won't pay any attention to that dotted line there, right? Because we know they're connected there, okay? So we could represent this the same way we've been doing all along, right? We could use an adjacency list, or we could even use an edge list, right? So those would be the traditional ways to do it, an adjacency list, or an edge list, or maybe even that matrix representation, if you remember. But today with union find, we're going to use grouping instead of an explicit graph structure. So what we're going to say is, hey, this graph right here is represented by a couple groups, and we're only going to store information about membership and nothing else, okay? So what we would be saying is this particular graph, this whole graph, has 3 components, right? And you might say, oh, well, how are they connected? And I'm going to say, sorry, I can't answer that question. I just know they're connected. I know this is connected to this, and I know all of these are connected, but I don't know how they're connected. That is the pro and the con of using groups as opposed to this more expensive representation that contains our topology, right? So the idea of edges are really only there when we add a connection, and then we sort of forget about that information and we just think about it in terms of the groups. Okay, that's where union find kind of hits its sweet spot. Okay, so we'll talk about things as groups, but if you go out and you read online, you'll often see these referred to as sets. So that's why they call it disjoint sets, right? These are disjoint sets, but we will refer to them as groups in our lecture and our quizzes and stuff like that, okay? So now, if you think about it, if this is all the information I have, is it okay to remove a connection, right? If I were to say, hey, I'm going to take 7 out of there, can I do that? Well, the problem is I can't do that, because look what happens if I remove 7, right? If I remove 7, in reality, now 0 and 1 and 2 and 3 form 2 different islands. But I don't have the topological information in here to actually even remember that they were connected in the first place that way, right? So this is why with union find, we say we're only doing additive connectivity. We cannot really subtract stuff, because otherwise we might end up with things that aren't really valid based on the original edge information we loaded up our data structure with, okay? So we might start with stuff like our data files for homework 6, But when we go ahead and we build this thing, our edge information is gone, right? And our union find can't really do anything except respond to adding of edges. We can't really remove any edges from that, okay? So let's take a look at how we put this thing together and sort of kind of how we theoretically represent that. And remember that we're talking about incremental connections. Like we can always add more connections and be very efficient at answering questions. So given some set of nodes, right, create or call a constructor to create some data structure, then we'll go ahead and kind of add our edges, but we're going to call it unify. So union find is all about unioning things together into these groups or sets. And that really, you can think of it as adding an edge, right? So if I unify 4 and 3, that's really kind of like having an edge between 4 and 3, okay? But all I'm really going to do is put them in a group together, okay? So the more I unify, you can kind of see the groups form dynamically, okay? And even though you and I can see the edges, the union find data structure, as we're going to see here in a second, just doesn't have any knowledge of the history of those edges. But it will remember who's in what group. And you can see that eventually, if I unify enough, it starts pulling these smaller islands together into bigger and bigger islands. So at any point, we should be able to ask a connectivity question and be like, hey, is 0 and 7 connected? No, it's not connected, right? So not yet anyway, right? So we keep going, we do more unifies, right? And eventually we get to a point where we want to ask a question again. Are they connected now? Yes, now they are connected. So we want this data structure to be able to answer questions in this kind of a real world situation where we're dynamically adding stuff, okay? So let's take a look at it purely from the group standpoint, right? So here is group 0 and here is group 145. So what are we going to call these things? They really are like connected components. So we could give them ID numbers, just like you guys are kind of seeing with your homework 6, right? Here's another group over here, right? And we cannot ununion these things, right? We can't say, oh, get rid of something. So that's just something we're going to have to deal with, okay? So it's just about connectivity, okay? So the group lets us know, yeah, you're in the group with me, so therefore we must be connected. That's the whole big idea. It's not really much more complicated than that, okay? So a couple operations here just to make sure we understand it. So we got some groups, right? And then we're going to ask questions about whether they're connected. Pretty obvious, right? If they're in the same kind of group together, we know they're connected, right? And if we gave these things numbers like group 0, group 1, group 2, and I said, hey, what's your group number and what's your group number, we could tell they're in the same group, right? Just like connected components. So that's the big idea with the union find, okay? Here's another couple representations, right? So we will give these things component IDs, and very often we will give it the ID of one of the nodes as a representation of uniqueness. It's like, okay, well, in this case, I'm not going to count from 0 up to the total number of connected components. I'm just going to use the ID of one of the nodes that are in that group, okay? So group 0, group 2, group 4, group 6. Seems a little arbitrary, but I'll show you why in just a second, okay? But we'll always have less than or equal to n groups, okay? So if everybody's in a group by themselves, of course, we'll have n groups there, okay? So we want to design this abstract data type more or less. So we're going to have a constructor to kind of create the initial nodes. We will ask what group or component ID you are in, right? So if I say, hey, I'm vertex or node 7, what's my ID? I will get an ID back and I can compare that with your ID, right? What group are you in, right? And then we can see if we're in the same group, okay? So X is not X is a node number. It's not some component ID, okay? So keep that in mind as we go. So if I say I want to unify two things, that's okay. We're adding a connection between two nodes or two vertices. So we're essentially forcing them into the same group, but we're also forcing all of their friends into the same group as well. So we are merging X and Y, but that is going to force all of their connections to become connected as well. Okay, so we're really not just putting them in a group together, we're putting all of their friends and friends and friends and all of that in a group as well. Okay, so that's one thing we want to keep in mind. Okay. So the total number of things in this group gets added to that, and one of these groups goes away, right? The former group that Y was in has to kind of go away, basically, okay? So that's our union part. And the is connected is just, what's your group ID? What are you in? And let's see if we're in the same group together, okay? So sometimes that's called the find operation. I like to call it is connected, okay? Sometimes it's referred to as are you in the same set, okay? And then if we count the groups or sets, right, that just says like, hey, how many islands or how many connected components do you have right now? So we're kind of seeing similar things in our connected component class, okay? So again, really all we care about is, are we connected? Can we talk on the phone together? Have no idea how long that path is, how many there are, but we'll use our union find to answer that, okay? And we'll have a get group, a unify, and then we can check also how many groups that we actually have. Okay, so each node is in only one group at a time, and when they're all by themselves, right, they kind of form their own group, right? If they have no connections anywhere, then they're in their group by themselves. So those are kind of our fundamental guiding principles. So let's take a look at this interactive one. So this is actually pretty good. So if you kind of jump on over to this, let me see if I can do this without using my screen share. So you're going to be in the union find or disjoint sets here. So if I pull up some examples, let me see if I can pull up something with 4 sets. Okay, and I say, okay, I want to find where is 0. Okay, so notice that 0 is at the bottom of what this tree looking structure. So what we're going to do with union find is come up with a way to represent groups by little mini trees. You can almost think of this as a forest, where each of these is a tree. And to answer the question about what group we're in, we just want to start on the thing we're curious about and follow it all the way up to its parent. And that's going to be the ID of our group. So as you can see, the ID of these groups is kind of basically the parent of the group. Okay. So this is how we're going to form the groups. These aren't really edges so much as they're just ways to sort of manage group membership, okay? So it's kind of kooky, but we'll see that it's actually really pretty efficient. So it's really just going to walk up to the top and figure out what's up at the top. But notice what it did there. While it was doing it, it realized that there was some compression we could do in that graph. So this is what we refer to as an eager algorithm. It said, oh, while I'm here trying to find who my parent is, I'll just sort of clean up the room here a little bit. And it shortened our tree. Okay, so this is compression, and we'll look at the code for that. It's actually pretty straightforward. But we're just taking the opportunity while we're looking for something to do a little restructuring. And that, again, that's referred to as an eager algorithm. Okay, so if I were to come over here to 11 and do a find for 11, right? We're saying, hey, what group are you in? On the way to actually doing that, it's going to find the parent, and then it should restructure that. Okay. And if I want to unify some things, right? If I say union or unify, I want to unify 3 and 5 here. So I'll bring this one down to 5. Okay. And we'll see there's a couple ways that we can do this, but really what we should do, we should see it put things together in a reasonable way. So it's going to plug the smaller group into the bigger group. Okay, this is a very efficient way of actually doing unify. So it kind of takes a guess and says, well, 3 is bigger, so maybe if I plug the smaller one into there, I won't have such a mess, right? If we did it the other way, we might have a lot more stuff and a lot more searching to do, right? So it is a little like a balanced search tree, not really exactly, but it's doing a little bit of work all the time to try to keep things in a reasonable, shallow tree. Because that shallow tree allows us to ask connectivity questions. Are you connected to you? Yes. Are you connected to you? Yes, right? So if we find that we're in the same group, then we know that we're connected, right? And if we're essentially in the same subtree is what it comes down to. So that's the name of the game we're after. You're welcome to come back there and take a look at that stuff. But our get group method is essentially going to be, find set, right? So we're figuring out whether these two things are in the same group or not, okay? And unify will be that kind of merging of those trees, okay? So feel free to play around over there. I won't kind of dwell on this too much, but you can look at different rankings and different examples where you can, see more complicated merging of these things, okay? So that is the union find. So let's take a look at our naming of groups again. So just reminding you that whatever node is at the top is going to be our component ID. So in homework 6, our component IDs go from 0 to up to some number, right? Less than n, right? But here they're going to be not in serial order, right? It could be whoever is at the top, right? So that's group 0, that's group 3, etc. Okay. So if I say, hey, what group are you in 0? It's of course going to be 0. If I say, what group is 1 in? It's going to be 0. So finding out the group you're in requires us traversing up from the leave to the parent, okay? Like so, okay? So that's our component IDs. Another way to think about it is, just looking at it like boxes. So this is probably overkill here, but you can kind of see what we're after here, okay? 2 belongs to group 2, etc. So when you're all by yourself, your group is named after you, okay? Again, get the group ID for 1, right? So that's going to be the 0, right? 1 is in the 0 group, okay? Okay. Any questions on that one? Pretty straightforward. Okay, let's talk about these connected real quick. Also, relatively obvious, right? If they're in the same group, then they're connected. So if I get the group ID for 1 and it's equal to the group ID for 0, they're connected, right? It's pretty straightforward. So getting the group ID is kind of fundamental to pretty much all the connectivity questions that we might want to ask. So if 2 and 4 are connected, it's going to be because they have the same group ID, okay? Just checking that, okay? And then 6 and 5, of course. 6 and 0, no, right? They don't have the same group ID there, okay? So that's the big idea. Okay, so unify. So just reminding you how unify works. If I unify 0 and 1, then we're moving one group into the other group. And really, we're going to have less groups, right? Less components. So 1 goes into the 0, for example. 2 goes into the 3. Let's say 5 goes into the 6, okay? Now, how we decide which one goes into which, for the moment, we'll just kind of always merge the first thing into the second thing, right? We'll just sort of pick something at random or just do it. But eventually we want to have this idea of choosing the smaller or the bigger group, right? Merge into the bigger group, okay? So we'll figure this out slowly, right? So this is our big optimization that we saw in that interactive thing on Visual Algo, right? It's like 3 and 4, who's bigger? Okay, well, even though I'm saying three into 4, right? 4 is smaller, so let's just move the 4 over here, okay? So that's a simple, but we'll see crucial optimization, okay? All right. Bigger groups win. So unify 4 and 1. So 4 and 1 is going to pull these two groups together, and we're going to pull group 0 into 3. Okay. So hopefully that's somewhat obvious. Okay. Now 0 is going to go away, right? There's no group 0 there, right? Okay. So there's our after merge. Okay. So I know this is a little obvious. We'll get through this here. So let's try just build a few things, right? Unify 3, 0. Okay. So now that group's gone. Unify 0 into 1, right? But 0 is the bigger group, so 1 should go over, right? And these are quiz questions, by the way. I know they're really straightforward, but if you understand this, you'll have no problem with this part of the quiz. 5 into 2, pick the bigger group, right? If it's a tie, then, pick some convention, so it really doesn't matter. And on we go, right? So eventually we're just merging these. So we're essentially hooking up trees, right? So let's look at a possible way to do this. We could try to use group IDs, right? We could say, oh, okay, well, what group ID are you in, right? So we could have some array of groups where each position of the array says what position what group each of our vertices is in. Okay, that would be one thing we could do, right? So this particular thing would be, 0 is in group 2, one is in group 2, 2 is in group 2, 3 is in group, right? So that's not bad, but if I merge something, two groups, I got to rewrite a lot of data in my group array, right? I got to actually go update a lot of the twos, okay? So it's got some drawbacks. It's quick to figure out what group you're in, but the maintenance of it, if we're in a dynamic environment, would be kind of expensive, okay? So unify in that case is kind of an expensive thing, right? We got to change a lot of stuff, okay? So not ideal, not ideal, okay? If we, over the lifetime, we've done this analysis before, right? If we choose the bigger group, we kind of only have n over 2 changes, but, it's still actually not great, okay? So get group is fast, right? Very quick to do, but, the maintenance from the modification is problematic. So what we want to do is kind of treat it like a tree, like we were seeing in Visual Algo, right? So we want to have essentially pointers, but we're not going to use, thankfully, C++ pointers. We're just going to use integer references, kind of like we do in our adjacency lists, right, where we refer to things by their ID, okay? So we're going to just have every vertex or node can potentially identify its parent. So 5's parent is, of course, 2, 2's parent is 3, 3's parent is itself. So we'll know that 3 is kind of the head of the group if it refers to itself, okay? So we're going to have a parent array that just says who everybody's parent is, right? We don't need more than n positions in a parent array in order to record all of our parents. And that way, when we unify, we're not changing a ton of stuff if we're pulling together two very big groups. So if we unify 1 and 2, right, we're really just saying, hey, 1, you are going to join group 2. So you're going to now kind of, a naive implementation would be like, your parent is 2, okay? And we're done, right? So that's a pretty quick union there to do, because it's just like, well, you told me to put them together, now they are, but in reality, 1 just joined group 3, okay? So that's like a little mini tree in the forest, okay? So these are called quick unions. Now, better thing to do would actually be to say, okay, well, here again, yeah, we're just doing the naive thing, right? We're just sort of saying connect, connect, connect. But the problem with this, as you can see, is if we just continued with these quick unions, we can get a very unbalanced tree, right? We can get a very, very long link there. And so it's not really going to maintain the performance that we want. The union part is really quick, but the kind of find group ID is going to be very slow, okay? Because we may have some super, super long chains there, okay? So we kind of like to find a middle ground so it's easy enough to figure out whether things are in the same thing, okay? Without these super long chains. So ideally what we want to do at first is say, okay, if I want to connect to 5, what I should really do is crawl up the chain on 5 and hook 0 directly into the parent, okay? So whenever we do a union, we'd like to just sort of follow the parent chain up and then do that connection there. And now we're not creating as much of a long, messy chain there, okay? So union 6, 5. So rather than it going to the bottom, we'll walk up the chain, and this means we got to figure out who the parent is all the time, right? So that's definitely improvement, right? So we're going to have everything kind of doing that, slightly slower unions, right? Because we got to walk up the chain all the time, but still definitely improvement, okay? So get group is, generally going to be just about walking up the chain, and that's going to be pretty fast, okay? So we can still do better though. So we're going to look at path compression. So the idea with path compression is, in addition to following the parent up to the top, we are also going to do some structural work in that process. So when I sort of unify 0 and 5, and I figure out, oh, 5's parent is 3, I will also do a little eager cleanup and rewire everything in that chain while I'm looking for the 3, or after I found the 3. And now it's going to be even better, right? Because now we've compressed the big long chain that was here, and we got the 0 pointing to the 3, okay? So that is compression on get group, okay? We'll look at that code here in just a second. So this is a pretty simplified kind of approach to finding and maintaining very efficient dynamic connections, right? We don't really know what that 6 was originally connected to 5. We just know that, they're all essentially connected to 3, okay? And we have a relatively short hop. So this is the union find, right? And we're going to use integer arrays to actually keep track of the parents. So that's going to keep things relatively simple. And we'll look at this eager, it's referred to as eager algorithm because it's going to do a little bit of work almost all the time, right? A little bit like our binary balancing trees, okay? And what that gives us, surprisingly, even in the most crazy examples, is essentially it's so flat that we are essentially maintaining constant time for all operations, basically constant time, which is pretty good. So let's take a look at just a couple of these. I know this is maybe a little tedious, but unify 9 and 5. We'll get the group on 5 is 3, right? And now, since we know what the group is by this get group kind of function, that just becomes our new parent, right? Okay. No compression needed in that particular case. 0.9 at the 3, right? And we're done, okay? So if I unify 10 and 8, we kind of want to put the 10 in the bigger group, right? So we get the 8, compress 7 on the way up, right? Because we notice that, to find the root of 8, we realize there's some work to do there, right? And now we can point the 10. And notice, by the way, this is a good slide here. Both the 7 and the 8 are getting compressed on our way to find the parent of 3, okay? Or parent of 8, right? And now we can kind of point the 10 at that. So the code is not really very complex about this at all, right? So one more here, 5 and 8. So we want to unify the 5 and the 8. Turns out they are all in the same group, right? So there's really no compression needed, and they're already in the same place, okay? So let's take a look at how we're going to actually do this. So we're going to need a parent array, the size of our graph, okay? And then we're going to say for I equals 0 to less than 7, we're going to just set each parent to itself initially, okay? So this is kind of helpful for the quiz and just in general for the algorithm. All of these are in their own groups right now because they're pointing to themselves as their parent, okay? And the parent of node 0 is 1, right? If we set that, right? And the parent of node 2, the parent of 1 is 2, right? So we're just sort of linking these things up to kind of show you how that works. So if I want to know whether these are connected, right, I have to traverse that graph. So this is essentially a way to represent a graph, right, where everybody has a parent, okay? So if we just kind of do this before the unify, right? So this is our graph structure. 0's parent is 3, 2's parent is 3, 5's parent is 2, right? So you can kind of see all of this is represented in this area here. And if I unify 6 and 5, right? This is what I'm going to do, right? I'm going to find the parent of 6, okay? The parent of 6 is 4, okay? Set the parent of 1 to be 5, because that's the parent of the 4, and there we go, okay? So no need for messy C++ pointers or arrows or anything like that. We'll just be doing this with our integer stuff, okay? So there's our update 1's new parent is 5, okay? Like that. Now we haven't done any compression yet in this. This was just kind of demonstrating how we use our parent array, okay? So that is a long seq, so that's something we want to actually clean up with compression, okay? And we'll do that here in just a second, okay? So here, let's just take a look at this, unifying 6, 5, right? So we'll find the root of 6, right? And then we will find the root of 5, and we will then update the 1 to point to the 3, okay? So slightly different than we saw last time. So rather than pointing the 1 at the 5, we're chasing up the path here, okay? And then the last thing we'll do is our compression. We'll come back to that in just a second, I think. So here's a typical question, right? Given the parent array, where each value in the array indicates the parent of the index, right? Determine the result of the function call shown below for the following parent. So here's our array right down here, get group of 6. So if we were going to get the group of 6, it's just kind of like that reverse path class. We're going to walk backwards from vertex 6. 6 goes to 8, 8 goes to 0, 0 goes to 3, and 3 stops at itself. So that's the top of the chain, okay? So the group that 6 belongs to is 3, okay? So we're just going to follow that thing backward until we find something that's self-referencing, okay? So number of quiz questions and Quizlets are like this, not that complicated, right? So if you understand the idea, you can work through these things pretty quickly, okay? Okay, so that's there if you want to take a look at that, okay? So if we look at this thing here, we can see we got multiple parents, right? So you should be able to tell pretty quickly that a number of these things are multiple parents, right? So I won't take you through all these, but you should be able to track back through these things and kind of pencil out a graph on paper from this, okay? And figure out what group we belong to, okay? So node 1 ultimately belongs to group 8, okay? Try that too. So let's take a look at the code for this. So here's our union find. So we're going to have a parents array. We're going to keep track of how big each group is so we can do an optimized merge, okay? So in other words, if I am going to merge two or unify two groups, I need to know that actually a particular group is bigger or smaller than the other one. So we're going to keep the size of these things, and we're just going to keep on hand how many total groups do we have. You know, is it n or something smaller than n, okay? We'll have a constructor, something that counts up the groups for us, our get group unify and is connected. So those will be really pretty much all we want to do there, right? And these will be our practice problems. We'll just quick work through these things. It won't be too heavy, I don't think. Okay, so here's our constructor. Nothing really earth-shattering here. We're going to create a dynamic array of integers. That's our parent array. This is our size of all the groups, right? And some of those groups are going to be of 0 size. So that means there are no groups for some groups, right? And then we will just go ahead and initialize everything, right? All the group sizes are 1. All the parents are themselves. Okay, and that's our constructor. And if we want to count the groups, we're just going to go through, and if we find a vertex whose parent is itself, right? If my parent is me, then I know I'm the head of a group, okay? So I can count out my groups, okay? Otherwise, we're just going to go through all of those things that way, right? So that's going to update our data member, and we can return that, or return that as a result of the method, okay? Unify, we're going to get the ID or the parent of A and get the ID or the parent of B. And if we're not optimizing this in any sort of a weighted way, it's pretty straightforward. We just say, hey, the parent of A is now B. We're going to add A's size to B's size and zero out A's group, right? So A is no longer going to be it's going to have group 0, right, for vertex A or group A, okay? Decrement our group count and return the actual parent of all of that, okay? So this is not totally optimized, but actually a pretty good way to go, okay? And we'll add some code to that here in just a second, okay? Oops. Leave that up there for a moment. Here at my code. Okay. So not really intense code. So we're going to do these real quick. We'll fly through these. You can kind of take a look at the code. We're going to finish implementation of the get group, the do compress, and the unify. There's just a couple lines of code in each. And we will merge A into B if it's unoptimized. Otherwise, we will figure out which one is larger and then, do the appropriate merge there. Okay. Which is essentially like saying if the group size of A is bigger than this, then we're going to merge B into A. Okay. Okay. Otherwise, we'll go the other way around. Okay. Okay. All right. So get group, pretty straightforward, right? We just got to kind of cycle through with a while loop. So it's kind of like following a linked pointer list, but we're going to be using an integer array instead of pointers. So the code should seem somewhat familiar to you. Okay. But first, let's look at main. How many nodes? Go ahead and create our structure. This is just a little debug thing I threw in there. Okay. And we will ask the user, we're going to build some random connections. So we're going to build a random array up here, a random network, and then we'll go ahead and print it out. And then we'll let you kind of ask questions, which node, which group are you in? Okay. And if you give me a bad node, then I'll crash the program. That's what our assert is there, right? But otherwise, we'll just say, hey, my group is that. Okay. So that's how we want to test it. Create it, and then ask some questions down here. Okay. So let's take a look at the code real quick. And the to-dos are there if you want to try to do a little bit of coding. So there's very little to do, in fact. So let's just dig in here. You put this on Moonlight mode and kind of make things a little bigger. By the way, the ad has been fixed. So I got an email today. If you see that ad show up anymore, let me know. They were very, very appreciative that we put up with it and told them that it was a problem. So I got a nice email today. So anyway, let's look for the to-do. Okay. So there's only really a couple of those. So inside of our get group, okay, we're going to say, given a particular node ID, right, what is my parent, right? So we're going to need a while loop in here to actually do this. So let me take you to that code, right? So while this node is not equal to its parent, in other words, we haven't reached the top of the chain, just say this node equal parents this node. So it's kind of like this node equals this node next, but we're just doing it with an array, okay? So we're searching for the top node in this chain of nodes represented by the parents array, and then we just got to return that, okay? So that's us following pointers through this parent array, okay? Okay, and then the next thing, so searching for our to-do again. Okay, I think, that's just the only one, I guess. Yeah, okay, just that simple. So that's our get group, okay? A lot like following a chain. And then eager is a terminology we use with certain algorithms where we know they're doing little bits of work all the time. So this is a classic thing you'll want to know coming out of algorithms class, whether something is eager or lazy. So this is just another example of something that's eager. So just showing you first off again what compression looks like. So here if we have this long chain and I am compressing from 7, right? It's just going to look like that. I started at the 7. I just ignored the 5, right? In that particular case, and just, pulled up the 7's pointer. Okay, so 5 is still kind of down there. Okay. And that is what we would do if someone said, hey, get the group for 7, because we'd sort of just follow the pointers up. We can't really go backwards with our current pointer structure. So it's not like we can kind of clean that up. Okay. Now, if I do that, then get group 7 obviously gets a little bit faster, and 5 gets a teeny bit faster, but it still could be better, right? We haven't fully compressed the 5 yet. But that's pretty eager, right? Now, if somebody said, hey, what's the ID of 5? Well, then we should do all of the cleanup all the way up the chain. So we should have that. So it sort of depends on where we start our get group from, right? So now any get group that we do is going to be a whole lot faster because we sort of compress the whole chain, okay? So we just compress as we go, okay? So we're going to write this do compress function, and we're going to put it in the bottom of our get group, okay? So if you think about it, I can't really compress unless I know who my parent is at the very top. So the first thing I got to do is loop up and find the parent, and then I can do the compression, okay? So we will call the do compress at the bottom of our get group method after we know what the parent is, okay? So we'll look at that code here in just a second, okay? So let's kind of hop in there, see if we can finish the do compress real quick, okay? Oops, come on, there we go. Okay. So here's our call to do compress. So what are we compressing to? So we're going to compress all the way up to the parent, but this loop is finding the parent node. So this temp node right here is an integer value that starts at the very bottom of the thing we're looking for, A, and we just keep searching for the parents, and then we know that that's what we want to compress to. So we want to compress from A to this node. So that's our compress function right there, okay? So, and here's the do compress. So you just say do compress from A to this node, right? So that's going to go right there. And then in this particular case, we're just going to have that while loop again. So let me take you over to our solution code, right? So there's our this node gets A, and while this node is not equal to the root that we're compressing up to, this is a little tricky. We're going to get a hold of the next node above me, and then we're going to aim this node's parent at the root. And then we'll be like, this equals this next, right? So we're moving up the chain. And so we're compressing as we go. Okay. So we just call that from inside of do compress, and now we've kind of optimized our chain a little bit, okay? So the loop is needed here so that we can compress everything on the way up, right? Everything between A and the root potentially gets compressed, okay? And that's our do compress, okay? So not too hard, okay? And then the last thing we're going to do is just add this little optimization. So if I have a group size of 4 and a group size of 2, we're just going to ask the question, who's bigger, right? So 2's group or 1's group, and then that controls how we actually choose the surviving parent, right? So if we keep the larger group in this particular case, we're going to just move that 6 over into the 3's group, right? So we're just going to move it down, connect it up, and off we go, okay? So that'll be a little modification to our unified code, okay? So let's take a look at this one real quick. So let me just pull up the to-do. We're almost there. We're doing on time. Good, we're doing all right, okay? So here's where we need to figure out who's the bigger group, right? So this is just some error checking code, but we need to figure out who's got the bigger group size. And this is why we keep track of group size, so we don't have to go count the groups every time we want to do a unify, okay? So rather than doing it just the same every time, we're going to actually do it slightly differently over here. So we're going to just kind of bifurcate our code here and say, if group size A is smaller than group size B, then the parent of A is now B, right? So we're pushing A into B on this one. So A is going into B because it's the smaller group. Otherwise, we do it the other way around, right? Otherwise, we're going to put the parent of B goes into A. Okay? B goes into A in that case. Okay. And that's our other optimization. Okay. So again, our performance, if we do these little kind of somewhat silly optimizations, essentially over the lifetime of working with this data structure ends up being constant. Okay? We kind of saw that with hash tables. If you remember, with hash tables, we were kind of able to keep our symbol table links somewhat short if we had a good hashing algorithm. So this is always the name of the game, is how to kind of amortize our costs over time. So all of these things are essentially constant. And if you want to really, if you really like math functions and you want to read about the Ackermann function, I mean, we will not do this analysis here, but there have been, proofs done that show that, yeah, this function, it is constantly growing, but it is so slow that it's never really going to get, it's like for a billion of n, it's like 5, right? So it's never going to really get very big in a real world scenario. Okay. Now, what do we use this stuff for? So that's kind of all you guys need to worry about. All this material is just referential, and then I'll kind of wrap stuff up for you. But I think this is pretty cool because you kind of look at this and go, so why do I care? Why would I want to use, union find other than some obscure algorithms? Well, basically, we can do model the porosity of physical systems pretty efficiently doing this. So the idea is we want to form this grid that sort of represents soil or electricity. So I worked at a 3D printing company where they were putting metal flakes inside of their resin for their 3D prints. And one of the questions they had was, is there going to be connectivity? What are the chances that all those little pieces of metal, enough of them are going to line up so that the 3D print can actually be used to conduct electricity? So it's really actually very hard to know the answer to that through, statistics, probability, and math purely without a computational model. So what we're going to do is kind of come up with this kind of a game where we'll say, okay, well, things that are black, we'll say, are not connected to anything. Things that are blue are kind of connected, but they're not sort of connected all the way through. We're going to imagine our flow of water wants to go through here, or our flow of electricity wants to go through there, right? So we have closed sites, and then open sites that kind of connect all the way to the top. And the way we usually do these kind of analysis, we talk about the probability that a particular site is being open. And that's the total number of open sites, these plus these, divided by the total sites overall. So that's our probability of being open, okay? So at some point, the porosity grows to the point where water or electricity or social media information flows through this massive network of connectivities. And we never really know how they're connected. Imagine Facebook, like somebody starts some, untrue thing and it moves through the whole Facebook social sphere. It's like, we don't know how that really moved through, right? Maybe we can analyze it. But at some point, if the connections are dense enough, then we know that that information is going to flow. And so that's what we want to study with percolation. We want to simulate gradually adding more and more open sites until we get percolation. And this has real world implications. So figuring out, again, with soil or electricity, et cetera, what is the level of porosity I need in order for information to flow through there, okay? So we will kind of do a real quick flyover on this, but we're going to slowly ramp up our probability until we know, using the union find, that the top is connected to the bottom, okay? And as you can imagine, we can just keep making more rows and columns and making our simulation bigger and bigger and bigger. We could even do a 3D volume simulation using this kind of union find graph structure. We don't care about the path. We just want to know if the top ends up being connected to the bottom, okay? So here's a site with 0 probability of percolation, right? So there's no chance anything's flowing through that thing. Over here, obviously, that's 100% probability because it's all open and connected top and bottom. And this is kind of somewhere in the middle. And we would calculate that probability as just the open sites over the total sites, right? 8 by 8. 64. So does it flow? Looks like it does. So 0.62 seems like a good value for flowing, but maybe I could go in this direction a little bit and figure out what's the minimum probability that I need to have for it to flow, right? So that's the game that we're generally playing, okay? And as it turns out, it's either not flowing or all of a sudden flowing. So this, what we call probability or site vacancy, is a very finely defined number. And it sounds boring and like a joke, but people want to know what that number is in a really bad way in a lot of different systems. And there's really only one way to find it, and that's by simulating it and simulating it with this union find approach, okay? So the idea is if we slowly open up or add more connections in a random way, jump around randomly like little spots in the soil, and we open things up and keep asking the question, can you hear me now? Can you hear me now? Can you hear me now? Right? Then eventually we'll get to that probability, and that's a scientific number that people really want to know for a particular scenario, okay? And it can apply to anything, right? It can apply to information travel, electricity, water, whatever, okay? So this is what game we're going to play. We'll sort of slowly add more connections and keep asking the question, is the bottom connected to the top? And we'll see how to do that here in just a second. But if I just focus on these two nodes, we can kind of see those things are connected, but we can use union find, right? And say, are they connected? If they are, then we have percolation. If they're not, we'll pick a random place, we'll add a connection, and then we'll ask the question again. How about now? Nope, not yet. How about now? Okay, now we have percolation. So this is called a Monte Carlo simulation. If we choose these connections randomly, we just sort of drop them in at random and we just keep asking the question over and over and over again. And that's what this particular kind of final thing is all about. And one of the nice things to take away from this, well, obviously, for one, we want to figure out what is that probability number. So we want to keep adding little connections until it percolates. And then we kind of have that information. But we are also going to need to modify our graph in a slight way so that we can run the simulation. Because as you can see here, there's a whole bunch of top sites and a whole bunch of bottom sites. So what we want to do, rather than checking every one of these top sites combined with every one of these bottom sites, is augment our graph with a source and target node. And this is a very common trick in graph processing. We'll see it again before the end of the semester. It's like, hey, I want to measure flow across this graph in this direction. So I'm going to create a little fake node here and here, and I'll just ask the question, do I have flow from here to here? And this is a really clever little trick that allows us to avoid this combinatoric kind of question asking thing. We're just like, hey, do my union find on that graph, right? Rather than checking every possible pair, okay? Because that would just get nasty, right? So this is our virtual sites, top and bottom. Okay, and now we just do that simulation. We just keep adding things, asking questions until we finally get some flow, okay? So we're not going to make you, look at the code necessarily or whatever, but it is pretty cool to see this thing just kind of works, right? So I'll show you a little sample here. You can just kind of watch it run. But we are really just connecting up these little spaces as we go through until we get percolation, and then we stop, right? Because that's when percolation happens and we measure our probability, okay? So we have billions and billions of possible connections in a large grid, right? So, but with constant time, optimization in there, we actually can do this in a reasonable way. Okay, so here's a real quick one. You can play with it or just kind of watch, but let me just run a quick sample for you here. So we're not going to really go too far with this, but if we wanted to run this thing, right, and just manually, oh, it looks like my code didn't load. Let's try that one more time. I know it's there. There it is. Okay. So if I were to run this, I can create a small simulation. So if I just want to do a 3x3, right, you can manually poke open sites into here. So I could say, put something at 0, 0, right? Now you can see I got an open space there. I can go 1, 0, right? Whoops. What happened? Oop, I think I mistyped something. Sorry. One more time. 3 of those. 0, 0. Okay. There's an open site. Row 1, 0. There we go. Okay. And then I promise I won't drag this out too long. Row 2, comma 0. And we get percolation, right? So the algorithm is working. So in our larger simulation, what is referred to as a Monte Carlo simulation is just do that over and over and over thousands and thousands of times until we actually get something to percolate. So I'll just run this one time for you. Okay. So I'm going to do a 10 by 10 and I'm just going to let it run, right? So it's going to go ahead and build all this stuff and you'll see it's slowly adding open sites until it gets to percolation, but it's constantly keeping track of what the probability factor is, right? And eventually we get down to the bottom and we'll see we actually get percolation down there at some point, right? There we go. So we finally got percolation, okay? I'm not sure quite where, oh, here it is. It's down, we're not quite there yet. There it is. All right, so we get flow through one of these, probably, it's kind of even hard to see actually where it went. Looks like maybe it got terminated by program IZ. Okay, so we ran out of processing space on that. Anyway, that if you open it up in REPL, you can kind of see that thing work. But just an example of how we actually do the union file. So I'm going to leave you with that. That's all we got for today. I will stay and help folks with your homework. Don't forget your quiz on Tuesday, and don't forget no class on Monday. So I hope you get an extra day to kind of relax a little bit. And thanks, everybody. I'll see you. Have a good weekend. Turn this off here.